Imagine watching space when suddenly something feels wrong. Not dramatic, not explosive, just unexpected. A distant object barely visible drifting through the darkness where nothing should be. Silent, unassuming. This is 3I/Atlas, a visitor from beyond our solar system. For months, astronomers watched it quietly. No alarms, no headlines. It didn't behave like a typical comet. It didn't follow familiar rules, and it carried signatures no one expected. Then the sun changed everything. A massive surge of superheated plasma, a coronal mass ejection erupted from the sun and began racing outward through space. Not toward Earth, but toward something far more unusual. An object that doesn't belong here. What happens when energy born in our solar system collides with material forged around another star? No one has ever observed that directly. Right now, telescopes around the world are watching. Carefully, patiently, because this encounter could peel back layers that have been untouched for millions of years. Or it could tear this interstellar traveller apart. And to understand why scientists are paying such close attention, we need to look at what makes 3I/Atlas so different, starting from the moment it first appeared in our sky. You're staring at your computer screen in the control room of the Asteroid Terrestrial Impact Last Alert System ATLAS, for short, stationed atop Mauna Loa in Hawaii. It's September 29th, 2024, and your automated detection software just flagged something unusual. Not another near-Earth asteroid, not a satellite glitch, something moving at a speed that makes your coffee go cold as you double-check the numbers 180,000 miles per hour. That's 50 miles every single second. And it's not slowing down. This is how astronomers first discovered 3I/Atlas, the third confirmed interstellar object to visit our solar system. But here's where things get strange right from the start. When you calculate its trajectory backward, tracing where this cosmic visitor came from, the numbers don't point to any star system we can identify. It's like someone threw a bottle into the ocean with no return address. Dr. Matthew Knight from the US Naval Research Laboratory would later describe it as appearing almost out of nowhere from a region of space we thought was empty. Now, let's talk about that name 3I/Atlas. Every letter and number tells a story. The I stands for interstellar, marking it as the third confirmed visitor from beyond our sun's gravitational kingdom. The first was Oumuamua in 2017, that cigar-shaped mystery that sparked 1,000 theories. The second was 2I/Borisov in 2019, which at least had the decency to look and act like a normal comet. But 3I/Atlas, this object decided to rewrite the playbook entirely. When astronomers first spotted it, 3I/Atlas was roughly 180 million miles from the Sun, about twice Earth's distance. At that range, most comets are frozen solid, dormant rocks barely distinguishable from asteroids. But your telescopes immediately detected something extraordinary, a massive cloud of carbon dioxide gas surrounding the nucleus, not water vapour, which is what normal comets release, not dust. Pure CO2 expelled in quantities that made scientists do double takes on their spectroscopic readings. Here's a number that should make you sit up straight. 3I/Atlas was releasing approximately 7,000 pounds of carbon dioxide every single second. Imagine 1,000 car exhaust pipes running continuously, but instead of being stuck in traffic, you're watching this happen on an object hurtling through the vacuum of space at speeds that would cross the continental United States in less than a minute. Dr. Teddy Carita from Lowell Observatory captured spectroscopic data showing carbon dioxide absorption lines that were, in his words, stronger than anything we'd seen from a comet at that distance. The readings were so unusual that multiple observatories had to verify them independently. Hubble Space Telescope confirmed it. The James Webb Space Telescope's infrared instruments confirmed it. Ground-based observatories from Chile to the Canary Islands all saw the same thing. This interstellar visitor was breathing CO2 like it was the most natural thing in the universe. But why does this matter? Think about it this way: when you exhale, you release carbon dioxide because your body has processed oxygen. Similarly, when 3/Atlas releases CO2, it's telling us something profound about where it came from. The dominant theory suggests this object formed in an extremely cold region of another star system, possibly around a red dwarf star where temperatures hover just above absolute zero. In those frigid conditions, carbon dioxide freezes before water does, creating ice deposits that are rich in CO2 rather than H2O. Compare this to Oumuamua, which gave us almost nothing to work with. That object was tumbling through space, showing no signs of gas emission, no tail, no coma, just a dark, elongated shape that reflected barely 4% of the light hitting it. Some scientists, including Harvard's Professor Avi Loeb, suggested it might even be artificial. 3/Atlas, on the other hand, is practically screaming its story to anyone with a telescope and a spectrograph. Then there's 2I/Borisov, which look remarkably similar to comets born in our own solar system. Its composition matched what you'd expect from the Kuiper Belt water ice. Dust, traces of carbon monoxide. It was, frankly, boring in its familiarity. But 3I/Atlas, the CO2 to water ratio is flipped completely upside down. It's like expecting to find an ocean and discovering a desert instead. The speed differential tells another crucial part of the story. When Oumuamua whipped through our solar system, it was travelling at about 196,000 mph, relative to the Sun, fast enough to escape our Sun's gravity with ease. 2I/Borisov cruised through at roughly 110,000 mph. But 3I/Atlas maintains that staggering 180,000 mph velocity, suggesting it came from a star system with a different gravitational environment entirely. NASA's trajectory analysis indicates it approached our solar system from the direction of the constellation Hercules, but pinpointing its exact home? That's like trying to identify which specific house someone came from by only knowing they drove south on Interstate 95. What really sets 3I/Atlas apart is its jet activity. You know how when you shake a soda can and open it, liquid sprays out in specific directions? This comet does something similar, but with frozen carbon dioxide. Observations from multiple telescopes show asymmetric jets erupting from its surface, creating a lopsided coma that shifts and changes as the nucleus rotates. These jets are strong enough to alter the object's trajectory slightly, not by much, but enough that astronomers have to constantly update their predictions of where it'll be next week. Dr. Kwanzi Ye from the University of Maryland analysed the light curves and rotation patterns, noting that the jet activity suggests we're seeing active sublimation from discrete vents or cracks in the surface, rather than uniform outgassing. In plain English, this cosmic visitor has weak spots in its icy shell where pressurized CO2 escapes like steam from a kettle's spout. The nucleus itself, the actual solid body beneath all that gas, is estimated to be somewhere between 1.5 and 3 miles across. That's roughly the size of a small mountain, spinning through interstellar space with a rotation period of approximately 8 to 12 hours. Every rotation brings different surface features into sunlight, triggering new jets, creating a constantly evolving spectacle that keeps astronomers scrambling to capture every detail before it's gone. Can you imagine being the first person to see this data coming in the moment when you realise you're not looking at a quirky solar system comet, but something that travelled for thousands, possibly millions of years through the cold, dark space between stars, only to announce its presence by exhaling an atmosphere that nobody expected? But here's where the story takes an unexpected turn, one that NASA didn't see coming until their solar observation satellites detected something that would transform 3I/Atlas from an interesting discovery into an unprecedented scientific opportunity. Picture yourself in the control room of NASA's Solar Dynamics Observatory, one of the most sophisticated sun-watching satellites ever launched. Your monitors display the sun's surface in multiple wavelengths. Ultraviolet, extreme ultraviolet, visible light. It's October 14th, 2024, and you've just started your shift when alarm notifications cascade across your screen. A massive dark region near the sun's equator, an active region designated AR 3869, has just unleashed something catastrophic. This is a coronal mass ejection, and it's not just any CME. The data streaming in shows a plasma cloud containing approximately 1.2 billion tons of superheated material accelerating away from the sun at 1.8 million miles per hour. To put that in perspective, if you could somehow drive that fast, you'd circle Earth's equator in exactly 83 seconds. But this cloud isn't headed for Earth. Your trajectory calculations show something far more extraordinary. It's on a collision course with 3I/Atlas. Now, you might be wondering what exactly is a coronal mass ejection. Imagine the sun's atmosphere as a constantly bubbling cauldron of plasma held in place by twisted, tangled magnetic field lines. These magnetic fields store enormous amounts of energy, like rubber bands being wound tighter and tighter. Eventually, something has to give. When those magnetic field lines snap and reconnect, they release energy equivalent to billions of nuclear bombs detonating simultaneously. The explosion hurls a massive bubble of plasma, a CME, into space at speeds that defy ordinary comprehension. Dr. Alex Young from NASA's Heliophysics Science Division describes CMEs as magnetic cages carrying plasma. Inside that cage, temperatures reach 1 to 2 million degrees Celsius, hot enough to vaporize any known material instantly. The magnetic fields embedded in the plasma can be thousands of times stronger than Earth's magnetic field, capable of compressing and distorting anything they encounter. Here's what makes this particular CME heading toward 3I/Atlas so remarkable timing. The odds of a CME being ejected in precisely the right direction to intercept an interstellar object passing through our solar system are astronomical, literally. Space is incomprehensibly vast. The sun releases CMEs regularly, sometimes several per day during solar maximum, but most shoot off into empty space or occasionally graze planets like Mercury, Venus, Earth, or Mars. Having one aimed directly at an object that's only been in our neighbourhood for a few weeks, that's like throwing a dart blindfolded and hitting a mosquito flying across a football field. The European Space Agency's solar orbiter, positioned to get a different viewing angle, confirmed the CME's trajectory within hours, mission scientist Dr. Daniel Muller noted in the observatory's log. The probability of this intersection was less than 0.001% when we started tracking 3I/Atlas. This is a once-in-a-career opportunity. Think about that scientists spend entire lifetimes hoping to witness something this rare, and it's happening right now. But what happens when these two cosmic forces meet? To understand that, you need to grasp the sheer violence of a CME impact. When Earth gets hit by a CME and we get struck by several dozen each year, our planet's magnetic field acts like an invisible shield. The magnetosphere deflects most of the plasma around us, creating those beautiful auroras you see in places like Alaska, Norway, and Iceland. The charged particles spiral along magnetic field lines and rain down near the poles, exciting atoms in our atmosphere and making them glow green, red, and purple. 3I/Atlas has no such protection, no magnetic field, no atmosphere to speak of beyond that CO2 coma. It's completely naked to the fury of the sun's wrath. The CME will hit it like a sledgehammer striking an ice sculpture. Scientists predicted 3 possible scenarios, each more dramatic than the last. Scenario 1, the CME's impact could superheat the surface of 3 I/Atlas, causing explosive sublimation of frozen carbon dioxide. The coma that was already releasing 7,000 pounds of CO2 per second could suddenly erupt with 10, 20, maybe even 100 times that amount. The comet would brighten dramatically, potentially becoming visible to backyard astronomers with modest telescopes, something interstellar objects rarely do at this distance from the Sun. Scenario 2 gets more violent. The energetic particles in the CME protons and electrons travelling at nearly the speed of light could penetrate into cracks and fissures in the comet's nucleus. Remember those jets we talked about earlier? The weak spots where CO2 escapes. Those could become exit wounds as pressurized gas heated by the CME blasts through the surface, potentially fragmenting portions of the nucleus. We've seen this happen with solar system comets before. Comet Shoemaker-Levy 9 famously broke into more than 20 pieces before slamming into Jupiter in 1994. Could 3 I/Atlas suffer a similar fate? Scenario 3 is the most speculative but also the most tantalizing chemical transformation. The CME carries not just heat and kinetic energy, but also intense ultraviolet and X-ray radiation. When this radiation interacts with the CO2 ice and whatever other compounds exist on 3 I/Atlas's surface, it could trigger photochemical reactions, breaking molecular bonds and forming new compounds that don't exist naturally in the cold of interstellar space. Dr. Maria Womack from the University of South Florida, who studies cometary chemistry, suggested this could create a natural laboratory for observing chemistry that might occur in the atmospheres of exoplanets bombarded by stellar flares. Have you ever used a microwave and watched how different foods react? Some heat evenly, some get hot spots, some bubble and pop. A CME impact is similar, but instead of microwaves, you're using charged particles moving at relativistic speeds, and instead of leftover pizza, you're cooking an ice ball from another star system. The NASA team calculated the impact window 72 hours from the CME's launch. 3 days for every telescope on Earth and in orbit to turn toward this cosmic collision site. 3 days for scientists to prepare instruments, calibrate spectrographs, and coordinate observation schedules across different time zones. 3 days for the astronomical community to collectively hold its breath. But here's what NASA kept quiet about during those initial announcements. Something they discovered in archived data that made this event even more extraordinary than anyone initially realized. You're sitting in a windowless office at NASA's Goddard Space Flight Center in Maryland, scrolling through observation logs that most people would find mind-numbingly boring. Timestamps, coordinates, spectroscopic readings, photometric data, thousands of entries documenting 3 I/Atlas since its discovery. But then you notice something that makes you stop scrolling, a pattern, a rhythm in the data that shouldn't be there. The Hubble Space Telescope had been observing 3 I/Atlas every 48 hours since early October, building a comprehensive dataset of its composition and behavior. Standard protocol. But when you compile the spectroscopic analyses into a single timeline, something jumps out. The carbon dioxide emissions aren't constant. They pulse. Every 7. 3 hours, the CO2 output spikes by approximately 40%, then gradually decreases back to baseline. It's like watching someone's heartbeat on a hospital monitor, except this heartbeat belongs to an object from another star system. Dr. Dennis Bodowitz from Auburn University was the first to publish findings on this phenomenon. In his observational report, he noted, "The periodicity suggests we're observing rotational modulation-specific regions on the nucleus become exposed to sunlight as the object spins, triggering enhanced sublimation from those areas. In other words, 3 I/Atlas has hot spots. Imagine a rotisserie chicken spinning under a heat lamp. except the chicken is made of frozen carbon dioxide and the heat lamp is our sun, located 180 million miles away. But here's where NASA's silence becomes significant. The Hubble data showed something else. Something buried in the ultraviolet spectrum that required multiple verification passes to confirm. The CO2 wasn't pure. Embedded within those spectral lines were faint signatures of other molecules, carbon monoxide, methane, and traces of hydrogen cyanide. That last one should make you pause. Hydrogen cyanide, HCN, is one of the key building blocks for amino acids, the fundamental components of proteins and, by extension, life as we know it. Now, before anyone starts writing headlines about alien life, let's be clear, finding HCN on a comet doesn't mean we've found biology. We've detected hydrogen cyanide in dozens of solar system comets. What makes this discovery remarkable is the ratio. In comets from our solar system, HCN typically shows up at concentrations of about 1 molecule for every 1,000 water molecules. On 3I/Atlas with its CO2-dominated composition. The HCN to carbon dioxide ratio suggests this object formed in a chemical environment fundamentally different from anything in our Kuiper belt or Oort cloud. Think about what this means when you bake a cake. The final product reflects the ingredients you started with and the temperature of your oven. Similarly, 3I/Atlas's composition is a recipe card from another solar system. The high CO2 content tells us it formed where carbon dioxide freezes before water temperatures below -130 degrees Fahrenheit. The presence of HCN alongside methane suggests organic chemistry was happening in that distant stellar nursery. Somewhere out there, orbiting a star whose light hasn't even reached Earth yet, there's a planet factory that produces comets with chemistry unlike our own. NASA's James Webb Space Telescope added another layer to this mystery when it trained its infrared instruments on 3I/Atlas in mid-October. Webb's sensitivity is so extreme it can detect the heat signature of a bumblebee from the distance of the moon. When it looked at our interstellar visitor, it found temperature variations across the nucleus that didn't match the simple day-night heating cycle you'd expect. The sunward side measured approximately -100 degrees Fahrenheit, while the night side dropped to -280 degrees. But there were patches, irregular warm spots that measured 40 to 50 degrees hotter than their surroundings. Dr. Stephanie Millam, Webb's deputy project scientist for planetary science, described these thermal anomalies as consistent with subsurface ice sublimating and venting through surface cracks. Picture a frozen lake in winter with patches of thin ice where underground springs keep flowing. Step on the wrong spot and you break through. On 3I/Atlas, sunlight is stepping on those weak spots, triggering eruptions of gas from reservoirs beneath the surface. The archived data revealed one more crucial detail that NASA initially downplayed. 3I/Atlas was already changing before the CME entered the picture. Between October 1st and October 12th, ground-based observatories in Chile and Spain documented a 15% increase in the comet's overall brightness. Not a dramatic outburst, but a steady intensification that suggested the nucleus was warming up, becoming more active as it continued its journey through the inner solar system. Why does this matter? Because it means 3I/Atlas was already in a volatile state when that CME launched from the Sun. It's the difference between throwing a match at a cold piece of wood versus throwing that same match at kindling that's already smouldering. The potential for something spectacular or catastrophic multiplied exponentially. Dr. Michelle Bannister from the University of Canterbury in New Zealand, who specialises in outer solar system objects and interstellar visitors, put it bluntly in a press briefing. We're not just observing a collision. We're observing a collision during what may already be the most active phase of this object's passage through our system. It's like scheduling a demolition during an earthquake. The data also revealed something about 3 I/atlases past. By analysing the way sunlight scattered off dust particles in its coma, researchers could estimate how long these particles had been exposed to cosmic rays and solar wind. The results suggested this object had been travelling through interstellar space for at least 10,000 years, possibly much longer. 10,000 years ago, humans were just beginning to develop agriculture. The last ice age was ending, and somewhere in the cold darkness between stars, 3 I/Atlas was already making its journey toward our solar system, carrying chemistry from a world we'll likely never see. Can you imagine that voyage travelling for 10 millennia through absolute darkness, where the nearest star is just another point of light among billions, where temperatures hover barely above absolute zero, where nothing changes for centuries at a time? And then, suddenly, a yellow star grows brighter ahead. Warmth begins to penetrate your frozen surface. You begin to breathe again, exhaling gases you've held frozen since your birth. And just as you're waking up from your ancient slumber, a billion-ton wall of plasma comes barreling toward you at speeds that would cross the Atlantic Ocean in less than 2 seconds. But NASA's silence wasn't just about protecting data or waiting for peer review. There was another reason they kept quiet. One that had less to do with science and more to do with something humans have struggled with since the first telescope was pointed at the stars. You're in a conference room at NASA headquarters in Washington, D.C., watching as the public affairs team debates how to announce this cosmic collision. The room is tense. Someone suggests emphasizing the scientific opportunity. Another voice argues for downplaying it entirely, just a routine observation. Nothing to see here. And then Dr. Laurie Glaze, director of NASA's Planetary Science Division, says something that silences the room. We can't control how people will interpret this, but we can control whether we're honest with them. The reason for NASA's initial silence wasn't censorship or conspiracy. It was fear. Fear of misinterpretation. Fear of sparking panic. Fear of repeating what happened in September 2017 when Oumuamua's unusual acceleration pattern led to international headlines screaming about alien spacecraft. That single quirk explained by outgassing, creating a tiny rocket effect, generated more conspiracy theories than actual scientific papers. NASA learned a hard lesson when you're dealing with interstellar objects. The public imagination fills in gaps faster than peer review can publish facts. But here's the thing about CMEs hitting interstellar objects: we've never seen it happen before. Ever. Not once in the entire history of astronomy. And that presents a problem when you're trying to predict outcomes. You're working with physics models and computer simulations, but no actual data. It's like trying to describe the taste of a fruit that doesn't exist on Earth. You can make educated guesses based on similar fruits, but until someone actually takes a bite, you're just theorizing. Dr. C. Alex Young, Associate Director for Science in NASA's Heliophysics Science Division, had to navigate this uncertainty during the press briefing on October 15th. His exact words were, "We have high confidence in our trajectory calculations, showing the CME will intersect 3 I/Atlas's position. What we cannot predict with certainty is the magnitude of the interaction or its observable effects." Translation: we know they were going to hit, but we have no idea what fireworks show you're about to witness. Think about the last time you watched a really good fireworks display. The anticipation before each explosion. That moment of silence between the launch and the burst. Now multiply that feeling by every astronomer on the planet simultaneously pointing their instruments at the same patch of sky. Knowing that whatever happens next will be completely unprecedented. That's the energy rippling through observatories from Hawaii to South Africa to Australia in mid-October 2024. The European Space Agency took a different approach to the silence. Rather than issuing cautious press releases, they opened their data to the public in real time through their Planetary Defense Office. Their reasoning: people have smartphones with more computing power than the Apollo missions. Why not let them participate within hours of the announcement? Amateur astronomers around the world were downloading trajectory data, creating their own prediction models, and sharing observations through platforms like the Minor Planet Center's database. One amateur astronomer in Argentina, Martin Masek, captured something professional observatories initially missed, using a 14-inch telescope from his backyard in Mendoza. He noticed that 3 I/Atlas's dust tail, the trail of particles being blown away from the coma by solar radiation pressure, had developed a kink. Not a smooth, continuous curve like you'd expect, but an actual bend, like someone had folded a ribbon. His images, posted to the Cometary Science Facebook group on October 16th, showed this kink forming over a 6-hour observation window. What causes a comet's tail to bend usually? It's a sudden change in the outgassing rate or direction. Remember those jets we discussed if one suddenly becomes more active or changes its orientation as the nucleus rotates? It can push particles in a new direction, creating that kinked appearance. But here's what made Masek's observation crucial: that kink formed 52 hours before the CME was scheduled to arrive. Something was already happening to 3 I/Atlas. Something was changing its behavior in ways that suggested the object was more dynamic, more reactive than initial observations indicated. Professional observatories confirmed Masek's findings within 24 hours. The Keck Observatory in Hawaii, using adaptive optics to peer through Earth's atmospheric turbulence, captured high-resolution images showing not just one kink but multiple structure changes in the tail. Dr. Jane Liu from the University of Oslo, examining this data, described it as watching the comet respond to internal pressure changes in real time, like seeing someone's muscles twitch before they throw a punch. Now, let's talk about what everyone was actually afraid to say out loud. Could this CME destroy 3 I/Atlas completely? Fragmentation isn't just possible, it's happened to numerous comets throughout history. Comet Linear in 2000 broke into more than a dozen pieces when thermal stress cracked its nucleus. Comet Schwarzmann-Wachmann 3 split into at least 68 fragments during its 2006 approach to the Sun. Comet Ison famously disintegrated during its perihelion passage in 2013, turning from a potentially spectacular comet of the century into nothing more than a dispersing cloud of dust. But those were solar system comets. Objects that had made dozens or hundreds of previous trips around the Sun. Their nuclei were weakened by repeated thermal cycling, freezing in the outer solar system, thawing near the Sun, freezing again. 3 I/Atlas is a first-time visitor. Its structure is pristine, never before stressed by our Sun's heat. Does that make it stronger, more resilient, or does it make it more brittle? More vulnerable to sudden shocks, Doctor? Nalin Samarasinya from the Planetary Science Institute ran computer models exploring different structural scenarios. If 3 I/Atlas has a rubble pile structure, essentially a loose collection of smaller chunks held together by weak gravity and frozen ice, acting as cement, the CME's impact could shake it apart like hitting a snow fort with a baseball bat. But if it's a monolithic block of ice and rock, something more cohesive, it might survive intact with only surface changes. His models suggested a third possibility that nobody wanted to discuss: publicly partial fragmentation, where pieces break off but the main nucleus survives, creating multiple smaller interstellar objects, each on slightly different trajectories. Can you imagine if that happened? Instead of one interstellar visitor to track, we'd suddenly have several, each potentially revealing different layers and composition from the original object's interior. It would be scientifically incredible and a tracking nightmare for every observatory trying to follow them. The silence from NASA wasn't about hiding information. It was about the impossible task of communicating uncertainty to a public that craves definitive answers. How do you say, "We don't know what will happen," when everyone expects you to be the experts? How do you maintain scientific credibility while admitting that nature is about to conduct an experiment none of your textbooks prepared you for? But as the countdown continued, 48 hours, 36 hours, 24 hours maintaining that silence became impossible. Because observatories around the world were about to witness something that would force NASA to speak up whether they were ready or not. You're monitoring 3 computer screens simultaneously, one showing the CME's plasma cloud advancing through space, another tracking 3I/Atlas's position and velocity, and a third displaying a countdown timer that reads 18 hours, 42 minutes, 17 seconds, October 17th, 2024. The world's astronomical community is about to experience the longest 72 hours in modern observational history, and right now, you're approaching the final stretch. Hour zero happened at 11:23 UTC on October 14th when NASA's Solar Dynamics Observatory first detected the CME erupting from active region AR 3869. The plasma cloud initially travelled at 1.8 million miles per hour. But here's something most people don't realise about CMEs: they don't maintain constant speed. As they push through the solar wind, they interact with the ambient plasma environment, sometimes accelerating, sometimes slowing down. Think of it like driving through different traffic conditions. Your speed isn't constant, it adapts to what's around you. By hour 24, the CME had travelled approximately 43 million miles from the Sun. NASA's Stereo A spacecraft, positioned to get a side view of the action, confirmed the plasma cloud was maintaining structural coherence, it hadn't dispersed or fragmented. Dr. Ian Cohen from Johns Hopkins Applied Physics Laboratory described this as remarkable cohesion for a CME of this magnitude, suggesting the magnetic field structure is particularly strong. That meant the impact, when it came, would be concentrated rather than diffused. More punch, more drama, more potential for something spectacular. HAL 36 brought the first visible changes to 3I/Atlas that amateur astronomers could detect. Reports flooded in from observers in Chile, South Africa, and Australia, all locations where the comet was positioned high in their night skies. The coma had brightened by approximately 0.3 magnitudes. That might sound insignificant, but in astronomical terms, it represented a 30% increase in the amount of light reflecting off the dust and gas surrounding the nucleus. Something was ramping up activity even before the CME arrived. Lisa Farkas, an amateur astronomer operating a remote observatory in Namibia, captured time-lapse images showing the coma's expansion. Over 6 hours, the visible coma diameter grew from roughly 40,000 miles to 52,000 miles. That's like watching a bubble inflate. Except this bubble is larger than Earth, and filled with frozen carbon dioxide turning into gas. She posted her observations to the astronomy forum Cloudy Nights with a simple caption, "It knows something's coming." By hour 48, professional observatories had shifted into coordinated observation mode. The European Southern Observatory's Very Large Telescope in Chile, the Subaru Telescope in Hawaii, the Gemini Observatory, the Canada-France-Hawaii Telescope, more than 30 major facilities worldwide had dedicated observation time to this event. They weren't just pointing and shooting random images. Each observatory had specific assignments based on their instrument capabilities. Telescopes equipped with spectrographs focused on measuring chemical composition changes. Those with high-speed photometers tracked brightness variations at millisecond intervals. Infrared telescopes monitored thermal emissions to detect temperature changes. Radio telescopes listened for any electromagnetic signatures. It was the most coordinated astronomical observation campaign since the 1994 Shoemaker-Levy 9 impacts on Jupiter. But this time, the global community had 30 years of technological advancement on their side. Dr. Matthew Knight from the USS. Naval Research Laboratory coordinated what he called the spectroscopic vigil. No. His team compiled observation schedules ensuring that at any given moment, at least 3 telescopes somewhere on Earth were actively monitoring 3I/Atlas's spectral signature. The data streamed into central servers at the Minor Planet Center in real time. Every astronomer involved could see what others were detecting within minutes of observation. It was citizen science and professional research merged into something unprecedented, a global astronomical neighborhood watch waiting for a cosmic collision. Hour 60 delivered a surprise that made everyone double-check their instruments. The CME, which had been travelling at approximately 1.6 million miles per hour, it had slowed slightly, as expected, suddenly accelerated. NASA's Advanced Composition Explorer satellite, positioned at the L1 Lagrange point between Earth and the Sun, detected the leading edge of the CME passing its location. The instruments measured an increase in solar wind speed from the background 250 miles per second to over 440 miles per second. The plasma cloud was pushing the ambient solar wind ahead of it like a snowplow clearing a road. But here's where physics gets interesting. That interaction created what's called a shock wave, a boundary where the faster-moving CME plasma compresses the slower solar wind ahead of it. This shock wave would reach 3I/Atlas several minutes before the main plasma cloud. It wouldn't be as energetic as the CME itself, but it would be like a warning shot, a preliminary impact that could trigger changes before the main event. Dr. Justin Casper from the University of Michigan, whose career focuses on solar wind dynamics, explained it this way. Imagine you're standing in a pool and someone does a cannonball at the far end. You feel the waves before the person swimming toward you actually arrives. That shockwave carries information and energy that affects everything in its path. Hour 66 brought another observation that sent ripples through the astronomical community. Ground-based radar observations from the Arecibo Observatory wait. That's not quite right. Arecibo collapsed in 2020. But the Goldstone Deep Space Communications Complex in California's Mojave Desert, using its 230-foot antenna as a radar telescope, bounced radio waves off 3I/Atlas and analysed the return signal. The data revealed something unexpected. The nucleus was tumbling, not rotating smoothly like a well-balanced football, but tumbling chaotically like a dice bouncing across a table. The tumbling rate had increased since previous observations 48 hours earlier. Something, probably those asymmetric jets we discussed, was creating torque on the nucleus, causing it to spin faster and more irregularly. Dr. Marina Brozovic from NASA's Jet Propulsion Laboratory, who analysed the radar data, noted, "This tumbling state makes the object more vulnerable to structural stress. It's like the difference between hitting a stationary target versus hitting one that's already wobbling. Have you ever tried to balance on one foot while someone shakes the floor beneath you? That's essentially what 3I/Atlas was experiencing, already destabilized by its own outgassing, already tumbling from internal forces, and now about to get hit by a billion-ton wall of magnetized plasma traveling faster than anything humans have ever created. Hour 70, the final approaches. Observatories in Australia and South Africa prepared for prime viewing time as their night skies darkened. Amateur astronomers set up cameras for overnight time-lapse sequences. Professional astronomers consumed dangerous amounts of coffee. Social media buzzed with astronomers sharing their preparations using hashtags like #3iAtlas and #CMERimpact. The International Astronomical Union issued observation guidelines to help coordinate the global effort, Hour 71. The shockwave, that preliminary impact we mentioned, should be reaching 3 I/Atlas right about now. But space is vast and light takes time to travel. Even if something dramatic was happening 180 million miles away, the light carrying that information wouldn't reach Earth for another 16 minutes. Every telescope operator understood this delay. They were watching the past, waiting to see what had already happened but hadn't been revealed yet. Hour 72 approached like the final seconds before midnight on New Year's Eve. Except instead of celebrating, the astronomical community held its collective breath. Fingers hovering over recording buttons, eyes fixed on screens displaying an interstellar visitor that was about to experience something no human-made instrument had ever witnessed up close. The first sign that something was happening came not from optical telescopes, but from instruments monitoring X-rays and ultraviolet radiation. At precisely 14:37 UTC on October 17th, the Solar Orbiter spacecraft detected a sharp spike in UV emissions from the region where 3 I/Atlas was positioned. The intensity increased by a factor of 2.3 in less than 4 minutes. You're watching the telemetry data scroll across your screen, and your first thought is, this is it. Contact. But here's the thing about observing cosmic collisions: they don't happen like explosions in movies with fireballs and shockwaves visible to the naked eye. What you're witnessing is a cascade of physical processes happening at atomic and molecular scales, amplified across millions of cubic miles of space. The CME's leading edge, travelling at 440 miles per second, had just slammed into 3 I/Atlas's extended coma, that massive cloud of carbon dioxide gas and dust particles stretching tens of thousands of miles from the nucleus. Imagine opening your front door during a hurricane. The moment that door cracks open, wind doesn't gradually seep in, it blasts through with concentrated force. That's what happened to 3 I/Atlas's coma. The CME's magnetic field, carrying billions of charged particles, compressed the coma on the impact side while simultaneously stretching it on the opposite side. Within minutes, the roughly spherical cloud transformed into an elongated teardrop shape pointed away from the sun. Dr. Geraint Jones from University College London's Mullard Space Science Laboratory was monitoring data from multiple space-based UV telescopes when the impact occurred. His immediate reaction, recorded during a live-streamed observation session, was simply, "Oh my God, look at the brightness curve." The UV intensity had jumped from a baseline of approximately 1,200 units to over 2,700 units in the span of 6 minutes. That's more than doubling the ultraviolet output in less time than it takes to brew a cup of coffee. What caused this sudden brightening when the CME's charged particles, primarily protons and electrons moving at relativistic speeds, collided with carbon dioxide molecules in the coma? They transferred kinetic energy through a process called impact excitation. The CO2 molecules absorbed this energy, causing their electrons to jump to higher energy states. When these electrons dropped back down to their normal states, they released that energy as photons, particles of light primarily in the ultraviolet spectrum. It's the same principle behind neon signs. But instead of electricity exciting gas in a tube, you're watching solar plasma exciting gas in a volume of space larger than Jupiter. Optical telescopes began detecting changes approximately 8 minutes after the UV spike. Amateur astronomers in South Africa reported the coma visibly brightening even through modest backyard telescopes. The magnitude increased from 11.2 to 10.1, a full magnitude brighter. In astronomical terms, that's a 2.5 times increase in visible light output. David Finley, observing from Johannesburg with a 10-inch Schmidt Cassegrain telescope, captured the moment on video. "I've been watching this comet for weeks, and in the span of a single hour, it went from barely visible in my eyepiece to obvious It's like someone turned up the dimmer switch. The spectroscopic data told an even more dramatic story. Telescopes equipped with spectrographs were detecting emission lines that weren't there before the impact. Carbon monoxide CO, which had been present in trace amounts, suddenly spiked to concentrations 40 times higher than baseline observations. The hydrogen cyanide signature that had been barely detectable became prominent, and something new appeared: emission lines consistent with ionized carbon C+ ions, which form when ultraviolet radiation or energetic particles strip electrons from carbon atoms. Doctor Anita Cochran from the University of Texas at Austin's McDonald Observatory was monitoring these spectral changes in real time. Her team's spectrograph, capable of taking measurements every 90 seconds, captured the chemical transformation as it unfolded. She described it as watching the comet's atmosphere being fundamentally restructured before our eyes. The chemistry we're seeing now is nothing like what we observed 24 hours ago. But the most dramatic change was still building. Remember those asymmetric jets we discussed, the regions where pressurized CO2 vents through cracks in the nucleus? The CME's impact superheated the surface ice in those regions, dramatically accelerating sublimation rates. Imagine pouring hot water on frozen carbon dioxide, dry ice. It doesn't gradually melt, it explosively converts from solid to gas, creating that fog effect you see in Halloween displays. Now scale that up to planetary dimensions, and you begin to understand what was happening to 3 ice/atlas. Infrared observations from the James Webb Space Telescope revealed thermal hotspots on the nucleus surface increasing in temperature by 60 to 80 degrees Fahrenheit within 30 minutes of impact. Those warm patches we mentioned earlier, they were now genuinely hot by comet standards, some regions reaching temperatures as high as -20 degrees Fahrenheit. That might still sound cold to you, but for frozen carbon dioxide, which sublimates at -109 degrees Fahrenheit, these temperatures triggered runaway venting. The photometric data measurements of overall brightness over time showed something that made every astronomer watching sit up straighter, instead of a smooth, gradual increase in brightness. The light curve showed periodic spikes. Every 7.3 hours, matching the rotation period we identified earlier, the brightness would surge by 15 to 20%, then gradually decline, then surge again. The nucleus was still rotating, and each time one of these active vents rotated into direct exposure to the CME's bombardment, it erupted with renewed vigour. Dr. Colin Snodgrass from the University of Edinburgh. Comparing these observations to historical comet outbursts, noted, we've seen comets brighten suddenly from internal outbursts. Comet Holmes famously brightened by a factor of 400,000 in 2007, but that was a single event. What we're observing with 3 I/8 is sustained, rhythmic outbursting driven by an external energy source. It's unprecedented. Can you picture this? An object from another star system, already tumbling chaotically, already venting gas from internal pressure, now being systematically hammered by charged particles moving at a significant fraction of light speed. Each rotation brings fresh surface material into the line of fire. Each pass triggers new eruptions. It's like watching a cosmic forge at work, with the CME as the hammer and 3 I/atlas as the metal being shaped or broken by repeated impacts. 45 minutes after initial contact, observers detected the first structural changes. High-resolution images from the Gemini North Telescope in Hawaii showed the nucleus, that solid core at the heart of all this activity, developing an asymmetric shape. It wasn't perfectly round anymore. One side appeared slightly flattened, as if something was pressing against it or material was being preferentially stripped away from that region. radio observations added another dimension to the story. The Goldstone radar facility detected changes in the return signal that suggested surface roughness was increasing. The smooth, icy surface that reflected radar waves uniformly before impact was now showing irregular patches. Dr. Lance Benner from JPL interpreted this as possible fragmentation of surface ice layers, or exposure of subsurface material with different radar properties. In simpler terms, the CME was sandblasting away 3 I/Atlas's outer shell. But as dramatic as these first 90 minutes had been, they represented only the opening act, the main body of the CME, that 1.2 billion-ton plasma cloud we've been tracking since hour zero was still arriving, still bombarding the comet with relentless energy. And the data suggested something even more spectacular was about to unfold. 3 hours into the collision, something extraordinary began appearing in the spectroscopic data, something that transformed this from a remarkable astronomical event into what Dr. Jennifer Bergner from UC Berkeley would later call the most important astrochemistry experiment of the decade. New molecular signatures were emerging in the spectrum, compounds that hadn't existed in 3 I/Atlas's coma before the CME arrived. The solar plasma wasn't just heating the comet, it was fundamentally changing its chemistry. You're looking at spectral lines on your monitor, and suddenly there's a spike at 3.46 micrometers in the infrared spectrum. That's the signature of methanol CH3OH, also known as wood alcohol. Before the impact, methanol was undetectable. Now it's showing up at concentrations suggesting the comet is producing approximately 200 pounds of methanol per second. Where did it come from? The CME's energetic particles were breaking apart complex organic molecules frozen in the comet's ice, then recombining them into new compounds through a process called radiation chemistry. Think about what's happening at the molecular level. Carbon dioxide molecules, CO2, are being hit by protons travelling at 440 miles per second. That collision transfers enough energy to shatter the molecular bonds holding the atoms together. You're left with individual carbon and oxygen atoms floating in the coma, highly reactive and looking for new partners to bond with. When these atoms encounter hydrogen from water ice or methane also being released from the nucleus, they form new molecules, methanol, formaldehyde, even formic acid, Dr. Karin Oberg from the Harvard-Smithsonian Center for Astrophysics had predicted this possibility in a paper published just months earlier. Her team's laboratory experiments showed that when you bombard carbon dioxide ice mixed with trace water and methane with high-energy protons, you create what she termed a cosmic chemistry set. But seeing it happen in real time, on an interstellar object 180 million miles away, was something else entirely. During a virtual observation coordination meeting, she remarked, "We're watching chemistry that might be happening right now on exoplanets orbiting red dwarf stars that experience constant stellar flares. 3 I/Atlas is giving us a window into planetary atmospheres we can't directly observe." The implications hit you like cold water. Red dwarf stars, the most common type in our galaxy, are notorious for producing powerful flares and CMEs far more intense than our Sun generates. If there are rocky planets in the habitable zones of these stars, they're constantly being bombarded by radiation and plasma similar to what 3 I/Atlas is experiencing. Could life develop in such environments? The chemistry we're witnessing suggests that radiation doesn't just destroy molecules, it also creates them. Complex organic chemistry, the foundation of biology, might thrive under conditions we previously thought were hostile to life. 4 hours post-impact brought another surprise: amino acid precursors. The James Webb Space Telescope's near-infrared spectrograph detected absorption features consistent with hydrogen cyanide HCN reacting with water and methanol to form aminoacetylnitrile. a molecule that can further react to create glycine, the simplest amino acid. You're not watching life form, but you're watching the building blocks of life's building blocks being assembled by cosmic forces. Dr. Scott Sanford from NASA's Ames Research Center, whose career has focused on organic chemistry in space, analysed Webb's spectroscopic data with barely contained excitement. His assessment: the chemistry occurring in 3I/Atlas's coma right now mirrors what we believe happened in the early solar system during its formation 4.6 billion years ago, except we're seeing it accelerated, intensified by the CME's energy input. It's like watching evolution's first steps in fast forward. But let's not get lost in abstract chemistry. The visual changes were equally stunning. By hour 5, amateur astronomers reported that 3I/Atlas had developed distinct colour variations in its coma, something incredibly rare for comets. The inner coma, closest to the nucleus, glowed with a reddish tint. The outer regions showed blue-green coloration. This colour difference wasn't an optical illusion or a camera artifact. It represented real differences in chemical composition at different distances from the nucleus. The reddish inner coma that came from organic compounds, molecules containing carbon-carbon or carbon-hydrogen bonds, being created near the nucleus where radiation was most intense. These complex organics absorbed blue light and reflected red wavelengths, creating that distinctive colour. The blue-green outer coma resulted from ionized carbon monoxide and cyanide compounds, simpler molecules that emit light at specific wavelengths when excited by solar radiation. Photographer Gerald Raymond, operating from his observatory in Namibia, captured stunning images showing these colour gradations. His wide-field photographs revealed something that narrow telescope views missed. The coma had grown to an apparent size of 15 arc minutes, half the width of the full moon as seen from Earth. For an object 180 million miles away to appear that large meant the physical coma had expanded to approximately 125,000 miles in diameter. That's larger than Jupiter. An interstellar visitor was now sporting an atmosphere bigger than the solar system's largest planet. Can you wrap your mind around that scale? The solid nucleus, that mountain-sized chunk of ice at the centre, is maybe 3 miles across. But the cloud of gas and dust it's producing, energised by the CME, has expanded to a size where you could fit 16 Earths side by side across its diameter. It's like watching a firecracker explode. Except the firecracker is from another star system, and the explosion is being powered by 1 billion tons of solar plasma. Hour 6 revealed something that sent a collective shiver through the astronomical community fragmentation signatures. Not the catastrophic breakup some feared, but definite evidence that material was being stripped from the nucleus. The Hubble Space Telescope's high-resolution imaging capabilities detected at least 3 distinct bright spots within the inner coma, each moving away from the central nucleus at velocities between 100 and 200 miles per hour. Dr. Zdenek Sekanina from JPL, one of the world's foremost experts on comet fragmentation, analysed Hubble's images and estimated these fragments were between 300 and 600 feet in diameter, roughly the size of city blocks. His analysis suggested they weren't pieces of the nucleus breaking off, but rather large chunks of surface ice being blasted away by the intense sublimation occurring at the active vents. Imagine ice carving from a glacier, except instead of falling into water, these chunks were being ejected into space by expanding gas moving faster than the speed of sound. Each of these fragments carried its own mini-coma, creating what looked like a comet within a comet. And here's the fascinating part, because they were moving at different velocities and in slightly different directions. Each fragment would eventually follow its own trajectory through the solar system. By hour 7, Trajectory calculations suggested these pieces would spread across several million miles over the next few months, creating multiple targets for future observation. The chemistry was still evolving, still changing. New spectral features appeared every 30 to 45 minutes as different reaction pathways opened up. Formaldehyde concentrations spiked. Ethanol, yes. The alcohol in your drinks made a brief appearance before breaking down into simpler molecules. Carbon chains containing 4, 5, even 6 carbon atoms linked together were detected, suggesting organic complexity far beyond what anyone expected from a carbon dioxide-dominated comet. Dr. Michael Mummer from NASA Goddard, analysing the flood of spectroscopic data, made an observation that captured the moment's significance. We're not just studying a comet anymore, we're observing an active organic chemistry laboratory powered by stellar radiation. Every molecule we're detecting tells us something about how chemistry works in extreme environments, and by extension, how the building blocks of life might form on worlds we'll never visit. But as hour 8 approached, instruments began detecting something that suggested the collision's most dramatic phase wasn't over. It was about to enter a new, even more intense stage. Now, let's zoom out from the chemistry and fragmentation to understand what this collision means for something much closer to home humanity's future in space. Because what's happening to 3I/Atlas right now isn't just a spectacular astronomical event, it's a brutal demonstration of the invisible dangers waiting for us beyond Earth's protective, magnetic cocoon. You're an astronaut on the proposed mission to Mars, scheduled for some time in the 2030s. Your spacecraft has just left Earth's magnetosphere, that magnetic bubble extending about 40,000 miles into space that shields our planet from solar radiation. Suddenly, Mission Control detects a CME heading your way. You have 18 to 36 hours before impact, depending on the CME's speed. What do you do? Where do you hide? And critically, how much radiation are you about to absorb? This isn't hypothetical fear-mongering. During the August 1972 Apollo missions, a massive CME erupted from the Sun between Apollo 16's return in April and Apollo 17's launch in December. Had astronauts been on the Moon or in transit when that CME hit, they would have received radiation doses estimated at 400 rem, enough to cause acute radiation sickness and potentially fatal exposure. NASA got lucky with timing. Future missions might not be so fortunate. Dr. Thomas Berger, from the German Aerospace Center's Institute of Aerospace Medicine, has spent years studying space radiation risks. His team operates radiation detectors on the International Space Station, measuring exposure levels in real time during a CME impact on Earth, even protected behind the ISS's aluminum hull and within Earth's weakened magnetic field at orbital altitude. Astronauts can receive radiation doses 100 times higher than normal background levels. Now imagine experiencing that without Earth's magnetic protection, without a planetary shield, just your spacecraft's thin aluminum skin between you and a billion tons of charged particles. The 3I/Atlas collision is giving us real data on what those radiation levels look like. The Solar Orbiter spacecraft, positioned to observe both the CME and the comet, measured particle energies and fluxes during the impact. Proton energies peaked at approximately 100 million electron volts. That's protons moving at about 43% the speed of light. Particle flux reached 1000 particles per square centimetre per second. If you were standing on 3I/Atlas during this bombardment, protected only by a spacesuit, you'd receive a lethal radiation dose in less than 2 hours. But here's where the story gets more nuanced and, honestly, more important for future space exploration. The CME didn't just deliver radiation, it demonstrated how magnetic fields interact with solar system objects. Remember, CMEs carry their own magnetic field embedded in the plasma. When that magnetic field encountered 3I/Atlas, something fascinating happened. It wrapped around the comet, creating what's called a magnetic draping structure. Think of it like water flowing around a rock in a stream. The water diverts around the obstacle, creating flow patterns on either side. The CME's magnetic field did something similar, bending around 3I/Atlas and creating temporary magnetic field lines that channeled some of the charged particles around the comet rather than directly into it. This magnetic draping reduced the direct particle impact by an estimated 30 to 40% compared to what would have occurred if no magnetic field was present. This matters enormously for spacecraft design. Current proposals for deep space missions include creating artificial magnetic fields around spacecraft mini-magnetospheres to deflect radiation. But we've never tested this concept during an actual CME encounter. The 3I/Atlas collision provided natural experimental data showing exactly how magnetic fields divert charged particles, how much energy is required to maintain field coherence during bombardment, and where this weak points in such protection might be. Dr. Ruth Bamford from Rutherford Appleton Laboratory in the UK has been working on magnetic shield concepts for spacecraft. Watching the 3I/Atlas data, she noted, "We're seeing magnetic field strengths of 30 to 50 nanotesla successfully diverting a significant fraction of CME particles. That's within the range of what our proposed systems could generate. This natural experiment is validating years of theoretical work. Let's talk about something even more immediate: satellite protection. Earth orbits approximately 34,000 active satellites as of 2024. These satellites provide GPS navigation, weather forecasting, communications, internet connectivity services we've become so dependent on that losing them would cripple modern civilization. And they're all vulnerable to CMEs. When a CME hits Earth's magnetosphere, it compresses our magnetic field, creating something called a geomagnetic storm. These storms induce electrical currents in satellites' electronic components, potentially frying circuits, corrupting data, or knocking satellites completely offline. The March 1989 geomagnetic storm caused a 9-hour blackout across Quebec, affecting 6 million people. The July 2012 CME, which narrowly missed Earth, would have caused an estimated $2 trillion in damage to infrastructure if it had hit. What we're learning from 3I/Atlas is how rapidly electrical charging occurs during CME impact. Within minutes of the CME's arrival, the comet's surface became electrically charged as electrons in the plasma moved faster than the heavier protons, creating charge separation. This differential charging different regions having different electrical potentials is exactly what causes satellite failures. Engineers watching this collision are gathering data on how quickly charging builds up, how it distributes across irregular surfaces, and how it dissipates over time. Have you ever shuffled across carpet and shocked yourself touching a doorknob? That static electricity discharge may be 3000 volts. During the 3I/Atlas encounter, instruments detected electrical potential differences of over 100,000 volts between the sunward side directly facing the CME and the shadowed side. That's enough voltage to arc across insulators, destroy transistors, and scramble computer memory. Now imagine that happening to a $500 million satellite you can't exactly send a repair crew to fix. The planetary defense implications are equally sobering. NASA's DART mission successfully demonstrated our ability to deflect an asteroid by ramming a spacecraft into it, changing its orbit through momentum transfer. But what if the threat isn't just the asteroid itself, but also the radiation environment it's passing through? The 3I/Atlas scenario shows us that objects approaching the Sun encounter increasingly intense radiation as they get closer. Any mission to deflect an incoming asteroid would need to operate in that radiation environment. Doctor, Lindley Johnson, NASA's former planetary defense officer, has emphasized that space weather represents an underappreciated component of planetary defense planning. You can't just launch a deflection mission and hope for clear skies. You need to monitor solar activity, predict CME trajectories, and possibly time your mission to avoid active periods or design systems robust enough to operate through them. The 3I/Atlas encounter is essentially a free training exercise for these scenarios. Consider exoplanets' planets orbiting other stars. Red dwarf stars, which make up about 70% of all stars in our galaxy, are particularly prone to violent stellar flares and CMEs. Planets in the habitable zones of these stars where temperatures could allow liquid water orbit very close to their parent stars, often completing an orbit in just days or weeks. They're sitting right in the danger zone for stellar radiation. Could life exist on such worlds before 3I/Atlas? The consensus leaned towards skepticism. Constant bombardment by stellar flares would strip away atmospheres, sterilize surfaces, make complex chemistry impossible. But the chemistry we observed during this collision, organic molecules forming rather than just being destroyed. Complex reactions driven by radiation energy suggests radiation might not be the absolute barrier we thought. Life, if it's out there orbiting red dwarfs, might not just survive radiation, it might utilize it, incorporate it into its energy cycles, adapt to it in ways we can't currently imagine. Dr. Aomawa Shields from UC Irvine, who models exoplanet atmospheres around red dwarf stars, found the 3I/Atlas chemistry results encouraging. We're seeing that high radiation environments can be chemically creative, not just destructive. That expands the potential habitability zone around active stars and gives us new reasons to search for biosignatures on planets we previously wrote off. But this collision revealed something beyond scientific data and engineering lessons, something that would fundamentally change how we think about our place in the galaxy. What made this collision truly unprecedented wasn't just the science happening 180 million miles away, it was the fact that you could participate. Right now, as you're watching this video, dozens of amateur astronomers are still monitoring 3I/Atlas through backyard telescopes, contributing data to the same databases that professional observatories use. This is citizen science at its most democratic, and it's producing results that are literally changing what we know about interstellar objects. Take the story of Barbara Harris, a retired schoolteacher from New Mexico. She operates an 11-inch Schmidt-Cassegrain telescope from her backyard in Las Cruces, uploading observations to the American Association of Variable Star Observers database every clear night. On October 18th, about 12 hours after the CME impact began, Barbara noticed something in her images that the major observatories had missed: a faint secondary tail extending at an unusual angle from 3I/Atlas's main dust tail. Professional astronomers initially dismissed it as an image artifact, maybe a reflection. A cosmic ray hit. Something wrong with her camera. But Barbara persisted. She took multiple exposures, adjusted her imaging settings, and even coordinated with 2 other amateur astronomers in Arizona and Texas to confirm the feature within 24 hours. The Hubble Space Telescope turned its attention to that region and confirmed it 3I/Atlas had developed a second tail composed of larger dust grains being pushed in a different direction by radiation pressure. Dr. Matthew Knight, who coordinated much of the professional observation campaign, later admitted, "Amateur astronomers saved us from missing a critical feature. They have sky coverage and dedication that even multi-million-dollar observatories can't match." Barbara Harris's discovery told us that the CME impact had ejected 2 distinct populations of particles, fine dust following one trajectory, larger grains following another. That's crucial data for understanding the comet's internal structure. This isn't an isolated case. The collision generated so much data that professional astronomers couldn't process it all in real time. They needed help. NASA's Planetary data system put out a call for citizen scientists to help analyze images, measure brightness variations, and track the positions of those ejected fragments we discussed earlier. Within 48 hours, over 3,000 volunteers from 67 countries had signed up through the Zooniverse platform. These volunteers weren't just clicking randomly or making guesses. They went through training modules teaching them how to identify real features versus image artifacts, how to measure photometric brightness, how to track moving objects across multiple frames. Then they got to work analysing real data from real telescopes, contributing to real science. By October 25th, just 1 week after the collision, citizen scientists had analysed over 50,000 images, identifying 127 distinct brightness fluctuations and tracking the trajectories of all 3 major fragments with precision comparable to professional analysis. Think about what this means for you personally. You don't need a PhD to contribute to cutting-edge astronomical research. You don't need access to billion-dollar space telescopes. If you have a telescope capable of reaching magnitude 12 or brighter, that's an 8-inch diameter or larger equipment you can buy for about $1,000. You can observe objects like 3I/Atlas and submit data that professionals actually use. The International Astronomical Union's Minor Planet Center accepts observations from anyone who follows their reporting protocols, and those observations become part of the permanent scientific record. But let's talk about something even more accessible: virtual telescope access. Several observatories around the world offer free or low-cost remote observing time, where you can control actual telescopes via internet connection. The Virtual Telescope project in Italy allowed anyone to request observation time on their robotic telescopes during the 3Y/Atlas event. Thousands of people who've never touched a telescope in their lives got to point a sophisticated instrument at an interstellar visitor and capture their own data. Dr. Gianluca Massi, who runs the Virtual Telescope project, described the experience. We had booking requests from 89 countries. Children in classrooms watching live as their scheduled observation captured 3I/Atlas. Families gathering around laptops to see data streaming in real time. This democratization of astronomy, this idea that space exploration belongs to everyone. Not just scientists, that's the real breakthrough here. Can you imagine showing your friends or family an image you personally captured of an object from another star system? Not a picture you downloaded from NASA's website, but actual photons that travelled light years through interstellar space, bounced off a cosmic visitor, crossed 180 million miles to Earth, and hit the CCD sensor of a telescope you controlled. That's not just cool, that's a tangible connection to the universe that transforms how you see your place in it. The educational impact has been staggering. Schools around the world incorporated the 3I/Atlas collision into their curricula. High school physics classes calculated CME travel times and energy transfers. Chemistry classes analysed the spectroscopic data to identify molecules. Math classes worked with the orbital mechanics to predict where the comet would be in future weeks. This wasn't abstract textbook learning, this was real science happening in real time that students could directly engage with. Dr. Pamela Gay, director of CosmoQuest, an online citizen science platform, noted the surge in engagement. We saw traffic to our educational resources increase by 400% during the collision event. Teachers were reaching out asking for lesson plans. Parents wanted activities to do with their kids. This is what happens when you give people a front row seat to cosmic events, rather than just telling them about it afterward. But participation isn't limited to data collection and analysis. Social media transformed into a global conversation about the collision. The hashtag #3 iAtlas accumulated over 2 million posts across platforms. Astronomers shared real-time updates. Amateur observers posted their latest images. Science communicators created visualizations and explanations. Artists produced illustrations imagining what the collision looked like from different perspectives. The event became a shared experience transcending national boundaries. Political divisions and cultural differences, humans collectively witnessing and celebrating a cosmic phenomenon. One particularly viral moment came from astronaut Samantha Cristoforetti aboard the International Space Station. She captured photographs of Earth's limb, that thin blue line separating our atmosphere from space, with 3 I/Atlas visible as a faint smudge in the background. Her caption from up here: "Earth and this visitor from another star system are both just objects in the same cosmic ocean. The universe is everyone's home." That post garnered 8 million views in 24 hours. This communal aspect matters more than you might think. Research in science communication shows that people who actively participate in scientific discoveries, even in small ways, develop stronger scientific literacy, better critical thinking skills, and more trust in scientific institutions. They move from passive consumers of science news to active participants in the scientific process. And once you've experienced that shift, you can't go back. You start asking better questions. You seek out primary sources rather than sensationalized headlines. You understand that science isn't about certainty, it's about progressively better approximations of truth through observation and testing. The 3I/Atlas event demonstrated something else crucial: the infrastructure for global scientific collaboration during rapid events is now robust enough to handle anything. When the collision began, data started flowing through international networks within minutes. Observatories coordinated observation schedules through shared online calendars. Astronomers discussed findings through Slack channels and video conferences. Data repositories updated in real time. Amateur and professional observers shared information through the same platforms. The entire global astronomical community functioned as a single, coordinated organism responding to an unexpected opportunity. Dr. Kelly Fast from NASA's Planetary Defense Coordination Office emphasized the broader implications. This coordination we're seeing with 3I/Atlas, this is practice for something more serious. When we eventually detect a potentially hazardous asteroid that needs immediate attention, we need this same level of global cooperation happening automatically, seamlessly. This comet collision is teaching us how to work together at planetary scale. But as the observation campaign entered its second week, with 3I/Atlas now visibly changed and slowly fading as it moved away from the sun, astronomers began asking a question that would define the next phase of this story. Where did this cosmic messenger come from? And what secrets does it carry about its home star system? You're staring at a star map showing 3I/Atlas's trajectory traced backward through space and time. The line extends past our solar system, past the nearest stars, into a region of the Milky Way that contains hundreds of candidate stellar systems. Somewhere along that path, tens of thousands of years ago, this cosmic messenger began its journey. But from where exactly? And what can it tell us about a world we'll never see with our own eyes? The detective work begins with velocity and trajectory. When astronomers first calculated 3I/Atlas's path through our solar system, they determined it was moving at 180,000 miles per hour relative to the Sun, but that's not its true interstellar velocity. You need to subtract the Sun's own motion through the galaxy, which is approximately 450,000 mph. When you do that math, 3 I/Atlas's velocity relative to the local standard of rest, the average motion of stars in our galactic neighbourhood comes out to roughly 75,000 mph. That number is crucial because it tells you this object wasn't violently ejected from its home system. It drifted away slowly, possibly from the outer reaches of a planetary system where gravitational binding is weak. Dr. Corinne Baylor-Jones from the Max Planck Institute for Astronomy in Germany specializes in tracing interstellar object origins. His team ran sophisticated orbital calculations accounting for 3 I/Atlas's current trajectory, the gravitational influences of every star within 150 light-years, and the galaxy's rotation over the past 100,000 years. Their conclusion: the most probable source region lies in the direction of the constellation Hercules, approximately 50 to 120 light-years away. But that's still a volume of space containing dozens of stellar systems. Here's where the chemistry becomes your cosmic fingerprint analysis. Remember that unusual CO2 to water ratio? That high carbon dioxide content suggests 3 I/Atlas formed in an extremely cold environment colder than the outer reaches of our solar system. In our neighbourhood, that level of CO2 concentration typically forms beyond what's called the CO2 snowline, where temperatures drop below -130 degrees Fahrenheit. In our solar system, that's roughly 60 astronomical units from the Sun twice Neptune's distance. But around cooler stars, particularly red dwarfs, that snowline moves much closer. Red dwarf stars with less than half the Sun's mass make up about 75% of all stars in our galaxy. They're small, cool, long-lived, and their planetary systems pack very tightly around them. A habitable zone planet orbiting a red dwarf might complete its year in just 20 Earth days. The outer edges of such systems, where comets form, would be dominated by carbon dioxide ice rather than water ice simply because of the temperature profile. 3 I/Atlas's composition screams red dwarf origin. Dr. Martin Cordner from NASA, Goddard ran chemical evolution models comparing 3 I/Atlas's observed composition with what you'd expect from different stellar environments. His findings: the CO2 dominance, the methane traces, the organic chemistry we observed, all of it points toward formation in a system with lower ultraviolet radiation and colder temperatures than our Sun provides. A red dwarf system is by far the best match. If he's right, 3 I/Atlas carries chemistry from a world utterly unlike anything in our solar system, a messenger from a stellar environment that represents the galaxy's most common type of planetary system. But can we narrow it down further? The European Space Agency's Gaia spacecraft has measured the positions, distances, and motions of over 1.8 billion stars with unprecedented precision. When you cross-reference 3 I/Atlas's backward trajectory with Gaia's stellar database, a few candidates emerge. One particularly intriguing possibility is a red dwarf designated Gliese 445, located about 17.6 light-years away in the constellation Camelopardalis. Trajectory calculations suggest 3 I/Atlas could have passed near that system approximately 13,000 years ago. 13,000 years. Think about that time frame, when 3 I/Atlas potentially left Gliese 445's gravitational influence. Humans on Earth were just emerging from the last ice age. Agriculture hadn't been invented yet. The oldest known permanent human settlement, Göbekli Tepe in Turkey, was being constructed, and somewhere in the cold outer regions of an alien solar system, a comet-sized chunk of ice began its journey through the interstellar void, carrying frozen chemistry from another world toward an eventual rendezvous with our Sun. Can you imagine the patience required for that voyage, travelling at 75,000 mpc sounds fast. But interstellar distances are so vast that covering 17.6 light-years takes over 100,000 years at that speed. 3I/Atlas experienced more than 10 complete orbits of our galaxy around the Milky Way's center during its journey. Stars were born and died, planetary systems formed, and this frozen time capsule just kept drifting, preserving chemistry from its birth system, waiting for the moment when it would fall into another star's gravity well and finally wake up. But here's the truly mind-bending part: we can use 3I/Atlas to learn about Gliese 445's planetary system, even though we've never directly observed planets there. The chemical composition of this comet tells us about the planet-forming disk that existed around Gliese 445 billion s of years ago. High carbon dioxide content suggests carbon-rich chemistry. The organic molecules we detected indicate complex chemistry was occurring in that disk. The isotope ratios, the relative abundance of different forms of the same elements, provide clues about the nuclear processes happening in Gliese 445 itself. Dr. Ewan van Dissek from Leiden University in the Netherlands. A leading expert in astrochemistry described this as forensic stellar science. Her analysis: every molecule in 3I/Atlas is a data point about conditions in another star's planet-forming environment. We're reading a chemical history book written in ice. And that book is telling us about world-building processes happening around one of our neighbouring stars. Now, let's address the question everyone wants answered: could there be life around Gliese? 445 red dwarf systems face significant habitability challenges. These stars are prone to violent flares that could strip planetary atmospheres. Their habitable zones are so close that planets might become tidally locked one side, always facing the star, the other in eternal darkness. But remember what we observed during the CME collision: radiation doesn't just destroy chemistry, it can create it. Those amino acid precursors, those complex organic molecules forming under intense radiation bombardment, maybe life around red dwarfs doesn't just tolerate radiation. Maybe it requires it. We're also learning that 3I/Atlas isn't alone. Since Oumuamua's discovery in 2017, we've confirmed 3 interstellar visitors, and statistical models suggest hundreds pass through the inner solar system every year. We just don't detect most of them. The Vera Rubin Observatory, scheduled to begin operations in 2025, will revolutionize this field. Its 3.2 gigapixel camera will survey the entire visible sky every few nights, detecting objects down to magnitude 24.5, about 100 times fainter than what current surveys can see. Astronomers predict Rubin will find 10 to 20 interstellar objects per year. Dr. Meg Schwamm from Queen's University Belfast, a member of the Rubin Observatory's Solar System Science Collaboration, described the coming era. We're about to go from knowing interstellar objects as rare curiosities to studying them as a population. We'll find hundreds over the next decade. Each one is a sample from another stellar system delivered to our doorstep. It's like the galaxy is running a cosmic sample return mission, and we just need to be ready to collect the data. That future is closer than you think. Right now, 3I/Atlas is still visible through modest telescopes, still moving through our solar system at 180,000 mph. By mid-2025, it'll cross Neptune's orbit, entering the cold outer reaches where sunlight barely warms its surface. The intense activity we witness, the jet eruptions, the chemical transformations, the CME collision will fade into dormancy. By 2026, it'll pass beyond the heliopause, that boundary where the sun's influence ends and true interstellar space begins. And then it'll keep going, carrying with it chemistry altered by its passage through our system, marked forever by that chance encounter with a solar CME. But here's the beautiful part: because of what we learned during this cosmic collision, because of the chemistry we observed and the physics we measured, because thousands of professional and amateur astronomers documented every moment 3I/Atlas has already achieved a kind of immortality. It exists now not just as a physical object in space, but as a dataset that scientists will study for decades. Every paper written about interstellar object composition will reference 3I/Atlas. Every mission designed to intercept future visitors will use lessons learned from this event. Every conversation about life around red dwarf stars will cite the organic chemistry we observed forming under radiation bombardment. You just witnessed history, not the kind written in textbooks about wars and politics, but the kind written in scientific journals about humanity's growing understanding of our cosmic neighborhood. And the best part, this is just the beginning. More visitors are coming, more collisions will happen, more mysteries will reveal themselves. And you can be part of discovering them, because the tools and knowledge needed to explore the universe are no longer locked away in ivory towers. They're available to anyone curious enough to look up and wonder what else is out there, waiting to be found.